Welcome to this lecture of game theory. I'm the lecturer Leonardo Badia. So in this lecture, we review some applications of the Nash equilibrium concept. And the applications I will cite can be found in, let's say historical literature, mostly about economics. So the purpose of showing this is, once again, not to give you something to memorize and blindly copy on your notes because you think at the exam there will be questions about it. There are two purposes to mention this. One is that sometimes these applications are so well known that you might find it quoted in some research papers even. And we will see examples of these applications, but I won't mention them already. But the main application of the tragedy of commons, which is one of the central applications we will see, is often quoted in many problems of resource allocation, even in engineering. So knowing what we are talking about would be useful to play smart when somebody quotes it. And the other reason is to give you inspiration, because the example we discuss here actually relate for the most to economic setups. But in reality, there is nothing that prevents you to apply this in an engineering context. And to be honest, I can tell you that a good 50% at least of the papers that you see in engineering who have game theory in the title, they are nothing new. They just take some economic scenario and apply it to engineering. So it's really a smart move in that I often call the repaint. It's like having, an old chair or an old table, and you repaint it with a brand new color, and it seems like it's something new and original. And since engineers are not very familiar with game theory, every one of these applications just transferred to the engineering context looks something new. But of course, this does not work for all possible scenarios, because we will discuss about markets, about prices, and so maybe the concept do not always fit, but if you find the proper translation, it can work. And also, this is even very useful to get a general understanding of the Nash equilibrium concept, because we reviewed some lectures ago the definition, and we even gave some examples like the fun game, but these were mathematics, they were theoretical examples. So, and it was good. I hope you master the concept of Nash equilibrium as a situation in which no one has regrets on what they did. And we will see this applied in other contexts. So we can reinforce our concept in our mind so we have it clear, because there are a lot of misconceptions about the Nash equilibrium concept. And so it's my intention that you have this clear in mind and can apply it well in your application of choice. Also, from a pure engineering perspective, what is the purpose of the Nash equilibrium? Well, Nash equilibrium is a prediction instrument, because we would like to see, this problem has a Nash equilibrium, and this looks like a good solution for the problem that we have in mind. That is, it's not really a solution in the classical sense. It's not really a mathematical procedure on how to solve the problem, but it's more like a prediction. Like you expect rational players will play a Nash equilibrium. So proving that there is a Nash equilibrium in a problem is like saying, well, we can predict how multiple players, multiple independent and sometimes even competing players will evolve. Okay, there are some problems with that. We discussed that some problems look like they don't have a Nash equilibrium. In reality, we can prove that there always is a Nash equilibrium, even when there seems to be none. We will see how to extend the problem so it always admits at least one Nash equilibrium. Well, there are some further problems, like in the battle of sexes, where there are multiple Nash equilibrium. So what to choose then? In this case, as I discussed, we would love to have some engineering intervention. So to engineer the problem so that the distributed players choose a specific Nash equilibrium among the possible ones. They are all equally good from the economic perspective, but maybe one of them is better. And we also discussed that we can quantify the price of anarchy or the price of stability So the price of stability can be lower because there is a better Nash equilibrium. And so we want to enforce this as opposed to the purely anarchical, very bad Nash equilibrium. Finally, we can have, in general, a non-efficient Pareto solution. A non-Pareto efficient solution as the Nash equilibrium, and this can be a problem. So sometimes it's worth quantifying how much do you lose because you allow this distributed management. And I mentioned some examples, and we will see some today. But in general, I even published some papers in which I quantify the price of anarchy. Well, the caveat about the price of anarchy, you have to remember, there are several ways of defining it. It all depends on how you define the total welfare or the total cost for the society. So there might be different possibilities of defining it. But saying that the price of anarchy is like 2 or 1.5 or 10 is a shorthand to say how much do you pay in terms of inefficiency because you are not using the optimal allocation, but you're using a Nash equilibrium. So if you're able to prove that a certain scenario has a price of anarchy, say, of 1.1, it means that you just lose 10% of your efficiency by allowing for distributed management. And this is a very good result engineering-wise. Of course, from the mathematical perspective, there always is a price of anarchy. But engineers say, well, maybe a price of anarchy which is 5% more, I accept. And the price of anarchy which is 150% more, I don't. So this is really an engineering judgment. And this is why also evaluating the efficiency of the Nash equilibrium is actually very important for mathematicians, for engineers. It does not, for applied mathematicians, it does not follow the realm of pure mathematics. Okay, very good. Then we can see some examples that in the literature are related to duopolies. So a reason why I mentioned in the introduction to the course that you should be familiar with the concept of monopoly or oligopoly is that the classic economic application is a duopoly. So you have two firms competing on the market, which happens to be often the case. Think of, the classic examples of Microsoft and Apple, or Coke and Pepsi, or Burger King and McDonald's. These are situations where you have two firms competing on the market, and they want to gain as many customers as possible. So the classic mathematic model is the Cournot duopoly, which was proposed by the French mathematician Cournot in 1838. And this actually is often cited as one anticipation of Nash results, because Cournot identified an equilibrium in his market that is actually the Nash equilibrium. And he did so more than 100 years before Nash. So the crazy part you have to understand about the Cournot duopoly is that it is an entirely wrong model, I would say. So it's a very abstract model. And, it's wrong in the sense that no real-world economy follows this model. But from the mathematical perspective, it's a very good model. And this is what I encourage you to do in any of your game theoretic analysis. That is, most of the times, engineers strive for a very accurate and very precise model where the utility function is very complicated and it gives a lot of factors into account. And this is often the criticism you receive when you show game theory results to a conference, for example. You say, my utility is this simple function. And this you did for the purpose of having simple computations, which, by the way, Cournot, found this model conceived this model in 1838. So it was sensible for him to have a very simple model because he didn't have any supercomputer back then. So he did do all the computations by hand. So it's a very smart idea to keep the model simple. And even if you have a supercomputer, it would be a good idea at the beginning, at least, to use a very simple function in your model. This is not wrong. It's a very good first step of an engineer. Then you can complicate as much as you want your functions. And then after that, you rely on the computational power of your computers, no more on the computations you do on pen and paper. But keep in mind that the mathematical functions we have seen so far, aside from very special cases, like there are some random elements involved, if the problem is purely deterministic, then the utility functions have no intrinsic value per se. They are not important in terms of precision and accuracy of the mathematical computation, because all that matters is that the bigger the utility, the more preferred the outcome. So you can really be a bit sloppy in defining the utility as long as you keep the order right. This is very important. And I'm sure that, well, when you will go to the model you conceive for your project, you will probably, the engineer in you will overtake the spirit of mathematical modeling. And will say, well, this model is not accurate enough. And so you go for a model with 300 variables, which is very complicated, but in the end, just has the same order of a much simpler model. This would be stupid of you. So don't do that. Keep the model simple. And so Cournot model is both very wrong and very right. It's very wrong in that it's very unrealistic, and I will discuss why. But it's very right in that Cournot was smart in keeping things simple. So Cournot wanted to model a duopoly in which there are two competing firms. We call them 1 and 2. So there are two players in a game. And they want to produce some good of a quantity. They are the sole producers. So they produce, I don't know, carbonated soda, and they are the only producers in the entire world. So customers either buy Coke or they buy Pepsi, either buy from producer 1 or they buy from producer 2. Now, Cournot model is like they decide the quantity they want to produce. So firm number 1 produces quantity Q1 of that good, and firm number 2 produces a quantity Q2. The total quantity is BQ equal to Q1 plus Q2. The cost to produce this quantity is the same for both firms. It's a function CQ, which is simple, a simple proportionality law. That is, there is a unit cost C, and if you want to produce Q units, your cost to produce them is C times Q. Very simple. And now when the good is sold on the market, you have a price on the market that is equal to A minus Q, where A is a constant. A minus BQ, you see, the function is here. Okay, now, more precisely, the price at which you sell cannot be negative because the lowest price you can give is 0. So you give the good out for free. So let's say there is a Heaviside function. This is a unit step, but that's just mathematical nitpicking. My point here is that every economist will laugh at you if you say this is the model, because that is not correct. That's not true. I mean, demand and law offer are much more complicated. There are Cobb-Douglas equations involved, but is it really important to keep these functions into account? No, it's not. Because all that we want to model here is that the higher the price, the lower the quantity, and vice versa. Remember, there is this general, holding for many, many goods, not for every good, but almost for every one of them, that the higher the price, the less you sell of this item. So ideally, here Cournot had this idea to simplify the computation to reverse the perspective. So companies decide how much to produce. And if they produce too much, then they know they expect the price will be lower. This is true from a purely mathematical perspective, from an abstract perspective. It's very wrong if you ask an economist, because companies do not decide how much to produce. They produce the amount that their firm establishment can allow. They have machineries, they have workers, and then they produce how much they can, and then they decide the price afterwards, right? So the real degree of freedom they have is to decide what is their price. And they will sell more or less of the quantity they have produced, depending on the price they set. Nevertheless, Cournot duopoly works like this. Take it as a mathematical model, a very abstract one. That is, very unrealistic in terms of accuracy, but very precise in modeling the key aspect. That is, there are two factors, the price that you sell on the market and the quantity you produce, and they are in opposite directions. So the more you produce, the lower the price. This is correct. So to us, from pure mathematical perspective, we are happy. And by the way, we are not economists, we are engineers, so we're happy enough with this simple model. Okay, so let's see how the Cournot duopoly works. The key aspect of the game is that the two firms choose Q1 and Q2 simultaneously and unbeknownst to each other. So it's like a static game of complete information. And once again, this is also an abstraction, because in reality, who says the two firms are not allowed to communicate with each other? They're not like in the prisoner dilemma put in separate cells. But maybe this is also a valid assumption, because even if they communicate, well, I will produce a lot this year. Maybe that's false. Maybe that's deception that your competing company will tell you. So you don't trust them. So actually, it would be best for the two companies to not communicate at all and just decide the quantity, the production quantity, independent of each other. Okay, so what is the Nash equilibrium? How can we formalize this game mathematically? So the strategy set of each player in the game will be a single move strategy. So because it's a static game, so your strategy is just your action as usually. So you can set any quantity in production from 0 to infinity, but you can discover there is no point in producing more than the constant A, because if you produce more than A, you will be forced to give the good out for free. So that's a stupid, you can prove it's a dominated strategy, so you can remove from the game already. In reality, it's a strictly dominated strategy, so you can remove from the game already. So you can say, well, it makes sense to simplify a bit the game and say the strategy set goes from 0 to A. It's just a set of numbers, okay? Now, if this is the case, the profit that you make is your payoff. And we assume, again, there is no risk involved, so we simply take the utility of a company as directly equal to its profit. And the profit is just the revenue minus the cost. This is very classical in economy. So if you take any economics first year textbook, they tell you, okay, you have the revenue, which is the money you make from the market, and the cost, which is the money you have to pay to go into the market. And so the profit you make is revenue minus cost. Simple. Now, if we put all this equation into place, we see that utility of player I depends on Q1 and Q2, and it is QI times the revenue, which is the price made by selling, and the price is a function of Q1 and Q2. This is very interesting because actually is what we wanted. This is a real game in that the two companies combine the decision, and in the market there is this merging point. Remember, the outcome must be depending on both actions or both strategy of the players combined. Otherwise, the problem is not very interesting. It's again a single player optimization. Now here instead you see that the cost is something that only company I pays, but the revenue depends on the price, which is a function of QI plus QJ. So even what the other player decided to produce matter to you, because if the other player is producing too much, the price will be very low, and so you make less money out of it. So this is the function you get as a result. If you substitute that the price is A minus total Q. A minus total Q means A minus QI minus QJ. Okay, so this is for player I, and you can revert for player J easily. Okay, is there any Nash equilibrium? How to compute a Nash equilibrium? Remember, we discussed that the computation of the Nash equilibrium can simply be finding the best response. So the only key difference from what we have seen, and you might have noticed, this previous slide can be like the normal form of the game because I listed the strategy set and the utility functions. However, I didn't give you any matrix. Why? Because the strategy set is continuous and not discrete. So we allow this one exception to the reasoning we made about the strategy set being usually discrete in game theory, at least for engineering problems. And this problem is actually the first example, is a quite historical example, and it is continuous, but it can be solved. So good for us. But generally, continuous problems have a lot of computational trouble, and I will discuss this in a while. For now, this can work even if it is continuous. So let's go with it. However, I cannot draw any metrics. That's the point. Okay, so to find a Nash equilibrium, I should reason similar to what I did, only I cannot go column by column because there is no matrix, there is no column. I can go for every choice of player 2 and look what is the best response of player 1. And also for symmetry reason, this also works in reverse. For every choice of player 1, I can identically find the best response of player 2. Let's see. For each player I, you must satisfy that that QI star is the best response, remember? So it might be that QI star is the argmax over QI of UI, QI, QJ star. The QJ star can be written as Q minus I, so it's the other player. The other player is playing a Nash equilibrium, and you must play a best response. Okay, that's by definition of Nash equilibrium. So seen otherwise to say, okay, I always compute my best response for whatever choice of any Qj, not necessarily a best response, but if this is a Nash equilibrium, not only player I plays a best response to J, but also this must be a best response to what I does. This is why I put this in red. Okay, so in the blue and orange are the two values. They are found as finding all the best responses to all moves of the other players, but the only condition I want is that they are both best responses. This one is, as written here, a best response, but also what I put inside here must be a best response. So I can compute this for any value in the right place, but I actually want to find not any green value for any value in the right place, but the specific blue value for which the red value is the orange value. That is, the blue value is the best response to the orange value and vice versa. Okay, so let's solve this equation. This is easy to find because if you want to compute the Qi, that is the argmax of this, you know how to do that. Of course, you are engineers, you have seen this, let's say, constrained optimization problem. It's not very difficult to solve. It's just a first, we take the first derivative because it's a very simple optimization of a single function. Keep in mind that now the concept of best response allows me to transform the problem, which is in general multiplayer, to a single player perspective, because the best response is a concept that is relating to one player individually. So I can take maximization. And well, in a continuous setup, it is first order derivative equal to 0. In a discrete setup, it's even simpler. You just go and list all the alternatives and you pick the best. There is always the maximum in a discrete setup because you have a finite set. You take the highest value, simple. In a continuous setup, things are a bit more complicated because sometimes I don't have a maximum inside an interval. So sometimes this doesn't work. But in this case, it works because I can simply take first order derivative and find Qi star as the solution of this equation. You see, I taken the first order derivative, which is, well, you take the derivative in Qi, it makes A, and here you have Qi squared, so it is 2 Qi star minus Qj star minus C equals 0. And the solution is kind of easy. You can write this equation actually for Qi and Qj, but for symmetry reasons, you can write it also for Qj and Qi. So you just swap the indices and you find out that the solution is Q1 star is equal to Q2 star is equal to A minus C over 3. So this is a number. I mean, A and C, I kept them in literal expressions, but you can put numbers. And then you have your optimal quantity, depending on the unit of measurement and everything. In any event, you solve the problem and you find that it is optimal for them to produce A minus C over 3. And this also leads to a given profit, which is the optimal utility, which is you can put this into the equation. You find it is A minus C squared over 9. If you don't believe me, just take the formula, stop the video and take the formula I've given like previous slide and put inside the numbers. You will see this is what you get. Okay. And of course, a stupid remark, the problem is symmetric for player 1 and 2. So we expected that the Nash equilibrium is also symmetric. That is kind of obvious consideration. The profit is also the same for the two players. Okay. Now, there is a remark you can make. This is for a duopoly case. What would happen if you have a monopoly situation? So for some reason, firm 2 disappears and the quantity they produce is 0. So now you can say that player 1 is left alone and can find the optimal monopoly quantity, which is denoted as Qm, which is this argmax, which is not the same as before. You see, Q2 now is equal to 0. So just to clarify, Qi star is computed as this argmax in which Qj star is present. So this is the best response to this, but this is also a best response to this. Qm won't be a Nash equilibrium because 0 is not the best response to Qm. It's stupid for a company to produce 0 because you sell for 0 and you get profit 0. So this is surely a better option in which you get a non-zero payoff. Also, the monopoly situation is interesting because it is the secret desire of each company. So from looking outside the mathematical perspective, if you are a duopolist, so a firm who has a competitor which is identically strong, what would be your desire? It would be that your company goes, the other company goes, your opponent goes bankrupt, and you're left the only one on the market. Maybe this is because you have a better situation. Let's see if this is the case. What happens if the other company disappears? You have the option of maximizing your profit by choosing this QM quantity, which maximizes your profit when Q2 is equal to 0. Okay, so this is easy again to compute. Now the QM quantity is A minus C over 2. And in which case your profit is UM A minus C squared over 4, which is higher than before. Earlier it was A minus C squared over 9. Now A minus C squared over 4 is much better. So good for you that you got rid of your pesky competitor on the market. You get a much higher profit. But there is another remark you can make, which is when you have the duopoly, the total production of the two firms combined is 2/3 times A minus C. Now that I have a single producer, the production is A minus C over 2. So is A minus C times 0.5, as opposed to A minus C times 0.667. So in short, the production quantity when you have a monopoly is lower. And why so? Because remember that old model with this crazy Cournot model was that the higher the quantity, the lower the price. So producing a bit less is a trick that the monopolist can do to increase the price. And increasing the price is very liked by the monopolist because they are the sole producer, so they can set a higher price. Of course, they don't set an arbitrarily high price, because if they do, the production, the only way to do so would be to produce 0 in this model. And so you still get a profit equal to 0. So this is the maximum, but still the maximum profit is achieved with a higher price than the duopoly situation. And this kind of confirms the intuition that competition is better for the customer, but worse for the producer, because each producer would be best off when being the monopolist. Also, the monopoly solution is kind of strange in that the total utility is more than twice the combined utility of the two duopolists. You see, the duopoly here gave each one of them A minus C squared over 9. So the total welfare of the two players, if we sum it, is 2/9. And 2/9 is a bit of times A minus C squared. And 2/9 is a bit less than 1/4. So, because it's 0.22 versus 0.25. So there is a loss in being in a competition for the two producers, which reflects in a gain for the customers, of course. And this is why, in general, when there is a monopoly, it is considered to be very bad by governments. However, keep in mind that so as I said, use this purple symbol QM and not Q1 star because it's a different allocation. So a monopolist would behave differently from the duopolist. And why so? Why can't one company say, well, I'm in a duopoly, but I don't care. I will produce QM anyway. Well, if they produce QM anyway, so A minus C half, they get a much lower profit because they are no longer alone. There is another competitor. And the other competitor will produce something more. So this won't be optimal in terms of revenue. Actually, the revenue, you can see it will be much lower. Still, so this is something that we already remarked. The quantity in the monopoly case is less than the duopoly production of the two firms combined. This is because if you have lower production, you have higher price and profit as a consequence, as South Park would tell you. Okay, now, you still can have a question in your mind. And if you don't, let me phrase it. Why don't the two duopolists agree on a trust? That would be a smart idea for them to do. So the trust case would be like this. Whatever I just said, like the monopoly case is better for the producer, and it's already, available as an information to the two companies, right? Because the two companies are assumed to be rational and smart players. So they can anticipate the result of their move. And they can see, oh, too bad, I'm not a monopolist. If I was a monopolist, I would have gotten a better revenue. However, a much better revenue, actually even more than twice the revenue I'm getting now. So one smart idea that the two companies can conceive is, okay, why don't we pretend like being a monopoly? We are not, because we are a duopoly. But if we pretend of being a monopoly, that is, we combine our moves, and of course we are two companies, so we split the monopoly revenue in half. We split the production quantities, we split the revenue, and so we split also the profit. As a result, we get half of the monopoly profit. Half of the monopoly profit is still higher than the duopolist profit. So it would be convenient for us. This would be like a collaboration. We act like if we are a monopoly, and we cheat the customers because we set a higher price. How would we do that? We set a lower production company. This would be similar to the prisoner's dilemma, right? We have two bad individuals that want to collaborate for their own sake and, well, for the sake of injustice. The two companies pretend being a monopoly, so they form a cartel, they form a trust. And they agree in producing less than the equilibrium. Their equilibrium production is A minus C over 3. But they agree on producing A minus C over 4, so that the total combined production is A minus C over 2, which is QM. As a result, the total profit they can share is A minus C squared over 4, and they divide that as well. They get A minus C squared over 8. A minus C squared over 8 is better than what they got in the previous situation, which was A minus C squared over 9. So why don't they do that? That would be, a good idea, at least from their evil perspective. And this, of course, is something that the government would like to prevent to happen. Well, good news, from the perspective of a Cournot duopoly, the two companies don't act like that. Similar to the prisoner dilemma. Even in the prisoner dilemma, the two thieves knew it was convenient for them to cooperate in terms of social welfare. But there is an incentive for unilateral deviation. So the trust case is not a Nash equilibrium because there is an incentive to deviate from such a strategy, a unilateral deviation. And this makes this a non-Nash equilibrium. Because QM half is not the best response to the other player playing QM half. You can see that the only situation where both players play a best response to each other is exactly the solution of the equations I've written here. So unless you play A minus C over 3, and the other player is playing A minus C over 3 as well, you are playing something, either of you is not playing a best response to the other. You can prove that this is the only Nash equilibrium in this problem, because this equation where you maximize the two conditions, you find Qi being the best response to Qj, and also Qj being the best response to Qi, so you write another equation with I and j reversed, you have a system of equations, and you have this only solution. It's a two equations, first degree system of equations, so you have only one solution. Okay, so very good. As a result, we can say that if the two companies think of, by the way, they cannot agree because they don't communicate, in my study is a static game, but they can sort of think, why don't we do this instead? It's all in their mind. Again, there is no communication, right? Still, they can conceive this strategy and observe it is a better strategy from the societal perspective point of view. It is Pareto dominating the Nash equilibrium, because in this situation, both get better. Still, in the Nash equilibrium, they don't have an incentive for unilateral deviation. No one of them wants to deviate from the Nash equilibrium, by definition. Here, instead, in the trust case, they want to deviate, because you can see that if one player plays QM half, which is a lower production quantity in order to keep the price higher, the other player has an incentive in producing more than QM half. Because the price is so high, it will make a bigger profit in increasing the quantity a bit. And so does the other player as well. The other player as well has an incentive in increasing the price a bit. So this is actually similar to the game we played with the crazy professor and betraying each other. Betraying each other gives an advantage to you and a disadvantage to the other player. You don't care about the other player. And especially, I mean, it might not be true when two poor students are at play, they care of each other because they're nice and loving, but the two thieves do not have honor among them. And the two firms, for sure, they don't care about the profit of the other company. They only care about their own profit. So if you try keeping the production level low because you want to keep the price high, you will discover that the other company will soon betray you and increase the production a bit so to have a bigger profit. So there is an incentive for unilateral deviation. And this causes the production level to be increased and increased and increased until you see the equilibrium is actually reached when you have you have A minus C over 3, which was Q star, the production level at the Nash equilibrium. So this concludes that, well, the Nash equilibrium is the only sustainable point in the market. The trust case would be more efficient for the two companies, but not sustainable. And that was interpreted by Cournot as a good outcome of the free market. This is also another reason why the company, are self-punished by their greed, because they act like the two prisoners in the prisoner dilemma. They betray each other because it is a better strategy to do so, and they end up in having a Nash equilibrium that is Pareto inefficient for them. Okay, however, you can argue, well, actually, I don't see that companies are in such a bad condition that the poor companies acting with competition, they don't try to cheat the customers. And you might be right. One possible explanation was given by Bertrand. Bertrand was another economist that said, well, you know what? Cournot model is totally wrong because the companies do not choose the price, do not choose the quantities, they choose the price. And this is a remark we made already. That would be a better model. So what happens if the companies do not set Q, but set the price, and Q is the result of the price setting? Well, in reality, this changes the game. So now, Cournot model can be argued if it's a good model or not, but still is a mathematical model. So as a mathematical model, it works like I have explained. So it's not wrong mathematically. Bertrand duopoly is another model. So let's consider Bertrand model. Then you can argue what's more realistic or not, but from the mathematical perspective, they're both precise and correct. Okay. Still, Bertrand model is entirely different. Now the strategies are the prices. So you set your price. And again, you use the same function, the same two functions of Cournot model, but in a different perspective. That is, the price is the strategy, and the quantity that you sell on the market is the byproduct of the prices. But the function is similar in that the price that is achieved on the market, you assume that if the two companies set different prices, well, people are not stupid. They will buy from the producer with lower price. So the function is the same. The quantity that you sell on the market is A minus the price, but this is true only for the cheaper price. The quantity sold by the other company will be zero. So there is a flavor of the battle of sexes. If they agree on the same price, they both sell. If they don't agree, only the one with lower price will gain some money. The other one will sell nothing. Okay, so if the prices are equal, actually, they share the quantity on the market. So they will sell a quantity A minus P, the same value of P, but the quantity of firm 1 will be A minus P over half, and so will be quantity Q2, because they split the market, okay? And once again, we say that the cost for producing a good is, unit cost is C, and again, we assume the profit is the same as before, is revenue minus cost. Okay, what do you expect to be the Nash equilibrium of this game? If you have now the gist of the problem, you will see what will happen, right? So the Nash equilibrium must be a situation where the prices are equal, first of all, because if the prices are not equal, someone will have regret. Well, the one with higher price will have a regret. So this cannot be a Nash equilibrium. Okay, but every pair of prices set that is equal can still have some regrets for either firm. Because let's say they agree on a very high price. You know what? Every company has a regret now, because they regret not having set a slightly lower price and they would have won the entire market instead of just half, correct? So there is a very old Uncle Scrooge McDuck tale in Donald Duck, where he competes against Rocket Duck for a market, and they sell, I don't remember, I think they sell beverages because they compete to see who is the best businessman, and they start selling $10 a piece, and then Uncle Scrooge decides to sell it for $9.99, so to gain the entire market. But Rocket Duck sells to $9.98, and so on and so forth. So they keep lowering the price until they reach a Nash equilibrium, right? So the Nash equilibrium is actually that you sell at production cost. So your price is C. You cannot go below C, because if you go below C, your revenue will be negative. Well, with price equal to C, your revenue is zero. Sorry, your profit is zero. Your revenue is equal to the cost. And so the profit is zero. If you go below that, your profit will be even negative, and it's not something you like. But this is also very strange. It seems like the equilibrium in a more realistic setup should be like, well, the price is just the cost. The firms just work for the sake of the goodness of their soul. They have a given cost in producing, I don't know, shoes or cars or whatever, and they ask you money without any surcharge. If there is a perfect competition, they will sell you the price of what they just paid. Well, this was lauded by Bertrand as a very good result, because it's clearly a bad outcome for the firms, and the customers are very happy because they pay a very low price. However, once again, let's look at this from the perspective of the Nash equilibrium. Well, the outcome is so bad for the companies because they make zero profit, but couldn't they agree on a very high price? Well, yeah, if they agreed on a very high price and they say, well, I mean, this could be the solution of the monopolist. The monopolist does not have this competition. So the monopolist can set a very high price. There is no risk for the monopolist to get the market stolen by a competitor because there is no competitor. So it would be maybe more convenient for the two companies to agree on a high price, more than C, and so make some profit. However, they can push the price very high up to a certain level, because if the price is too high, they will sell nothing. So this is the value. So they can increase the price over C. You can find that they cannot push the price beyond A plus C half, because if they go beyond that value, the revenue will be zero anyways, because they sell nothing. Because remember, the price they sell is, the quantity they buy is A minus B. But nevertheless, they can increase the price and make some revenue out of it. However, this is not a Nash equilibrium, because the Nash equilibrium will imply that no firm has regrets. So if they agree on setting a much higher price, there is an incentive for each one of them to betray the other by setting a slightly lower price. And so this can be argued as a criticism of a Nash equilibrium in real situation. You can say, well, probably the two firms are not rational, or the customers are not rational, because sometimes they buy things from a firm when the price is higher. They don't buy only discount products. So of course, this was applauded as a very good result for the market economy, because ideally the companies should go for a very low price. Actually, they shouldn't make any profit at all. And this is kind of unrealistic, by the way, and we will discuss this in a while. But let me remark that in the real world, here is a consequence of the mathematical assumption. It is, if you see two companies selling, if they are closest shelf by shelf, you see two identical products. One is sold at 10 euros, and the other one is sold at 9.99 euros. You buy the second one, of course, but most of the times you buy the one that is most convenient for you. We'll discuss this in a while. However, let me make another remark, which is that in general, you should have zero profit as a company in the Bertrand duopoly. And this is a consequence of the rationality of the players. So the two players are perfectly rational. And if they believe the other firm is setting a given price, they should set a slightly lower price than this. So the only way to counteract this is to set a price equal to C, which prevents the other company to set a lower price. Because as I mentioned, you don't set a price lower than C. because that will cause you a negative profit. By the way, if you set C, or if you believe the other player is setting C, what happens? You say, well, my best response is anything, because whatever I do, I get zero revenue anyway, right? Because either I sell again at price C, in which case my revenue is zero, because it costs me CQ to produce it, and I sell it for CQ. So the revenue is equal to the cost. Profit is zero. Or I set a higher price than that, but nobody buys from me. So my revenue is also zero. Okay, well, this is true as long as your price is bigger than C, because if your price is lower than C, you get a less than zero profit, which is undesirable. But it means that if you believe the other player is playing C, you're actually indifferent for among any value of price that is greater than or equal to C. However, you might think, oh, then any situation where the other firm is producing C and I'm producing more than C is the Nash equilibrium as well, because I'm playing another best response. Remember, best responses are not unique. So it is the best response to C is not just C, it is also any C plus epsilon is also a best response. Well, the problem is this is not a Nash equilibrium, so because C is not the best response to C plus epsilon, correct? So if firm one increases the price, the profit will be zero for them anyways. But firm two will have a regret now, because firm two thinks, well, I should have increased my price a bit and I would make an even bigger profit. The other guy will make zero anyways. So you see there are some problems here, and they depend on this, how much can you distinguish between bigger and lower prices? Especially there is a problem I will discuss in a while about the continuity of the space of the function. But as I was discussing, there is a problem of realism as well. The usual explanation you see in economics is that, well, if you have two perfectly identical goods that are sold side by side in the supermarket, and you see the prices are different, of course, you buy the lower one. You will be stupid to buy the more expensive one. But in reality, substitutes are never perfect. The two goods are imperfect substitutes of each other. So you can argue, well, I don't know, I still prefer Coke over Pepsi, so I don't care if Coke is a bit more expensive, but I don't like the taste of Pepsi, so I want to buy Coke anyways, or vice versa. And this explains why there are sometimes, fake brands in the supermarket. You see like a very expensive, brand of cookies, and you see side by side on the shelf of the supermarket a similar cookie with a much lower price. Well, you don't buy it maybe because you don't like, it's going to be, a lower quality cookie. So this is explained by Bertrand if you change the rules of the game. So this is another game, but is a better realistic model, but also a more complicated one. So again, do not consider the Bertrand model as a very realistic explanation. It's just a mathematical model. And you, of course, can have a better mathematical model, which is more realistic, but also more complicated. What happens if you have a parameter B that is a sort of exchange rate between the goods? And B, for some technical details I won't explain to you, is this B must be less than 2, but the computation goes like this. The quantity that you buy of a good I depends on the price of I. So the higher the price, the less you buy of this good. But it's also a function of an increasing function of Pj. What does this mean? Remember, the two substitute goods are related so that you buy more of a good if the price of the other good increases, correct? And this means that if you increase price Pj, it's not like you buy zero of the one with higher price. You buy a little bit of both, but the quantity you buy of a good I also depends on the price of the other good in an increasing fashion. So your quantity of I decreases with Pi, but increases with Pj, correct? So the point is here that we want to model the substitute relationship in a better way. If they are perfect substitute, you just buy the cheapest. But if they are imperfect substitute, you buy a bit of both and the share you buy of one quantity or the other depend on the exchange rate. So B implies that the bigger is B, it means the more difficult it is to substitute. So every little spike in the price of good J makes you buy almost exclusively user I. But B can be lower and so compensate for the two of them. So you can show that in this situation there is a Nash equilibrium that is more familiar because it's A plus C divided by 2 minus B. Remember, this was similar equation that we saw in Cournot duopoly, and now it depends on the value of B. So B can even be negative, and if you have B equal to -1, you have A plus C over 3. I mean, this is the price actually, not the quantity, but still you have similar equations. So I won't discuss this in more detail because this is outside the scope of my interest here, but I just want to mention that economists are not that dumb to believe that the allocation on the market is just zero revenue for the companies, zero profit for the companies. It's actually more realistic than that. There are better models than that. And of course, they take into account that, well, maybe you can buy a service in 2 different places and you discover that service place number 1 has a slightly more expensive service, but it is more convenient to go to service number 1 anyway. Like a classic example is, I don't know, gas pump. If you go to a gas station, you see, I mean, you have a cheaper price in another city. Well, you don't travel there because it will cost you more in gas to travel there than the amount of gas you save by refueling in your town. So this is, again, a more complicated model, and I'm not implying that this is a realistic economic solution. I'm just giving this to you to explain to you the concept of game theory, because you see now how powerful is the idea that we should look for an allocation where no one has regrets. Okay, another thing that is worth discussing about Bertrand duopoly is the case with different costs. Because in the case with different costs, you are in trouble for the company with higher cost. Actually, there is no way the other firm, in this case, if C2 is higher, well, one has an advantage. And there is no way that firm 2 can win. Because in this simple situation, firm number 1 can set the price any value lower, strictly lower than C2, and they will win because they will be the monopolist. So the slide said one possible Nash equilibrium is 1.99 and 2. Well, 2 is still the best response for player 2 because player 2 has cost equal to 2. So the best response for player 2 is still to play the cost. But playing the cost will not give them any profit. However, if they set a lower price, they get negative profit, which is even worse. If they set a higher price, remember, you will see that C1 can then have regrets. So this cannot be a Nash equilibrium because C1 can push the price higher. The key point here is this 1.99. I should really write something like 2 minus epsilon, where epsilon is the lowest granularity that we can allow in prices. So I put 1.99 because the lowest granularity we can have in Italy, at least, is Eurocent. You cannot say, well, my price can be 1.999 because there is no sub-multiples of 1 cent, right? So the key problem here is really this role of epsilon. If your granularity tends to 0, so you have a really continuous problem, you are in trouble because then 2 and 2 is not a Nash equilibrium, because if you have 2 and 2, company number 1, despite having a lower cost, and so the advantage of possibly being a monopolist, will not accept that. So 2 and 2 implies they split the market. And why should firm 1, who can be the monopolist, want to split the market? They don't want to. So in 2 and 2, firm number 1 has a regret. So the Nash equilibrium should be 1.9 something with lowest possible granularity. But if the value is continuous, this problem has no Nash equilibrium, basically. So this is also a very tricky problem, and it's often the solution is to use discrete space values. And again, I mentioned that we will concentrate only on discrete space values from now on, more or less, because it's much easier to consider discretized state spaces where you don't have this kind of problem. I mean, and that's also true in real world economy, because prices cannot be continuously split. You cannot charge somebody who don't eat to the restaurant and they tell you well, you know why you owe me 20 pi euros. They must stop at the second decimal digit, right? So they cannot go on indefinitely. So in reality, this is a Nash equilibrium in the real world where you have a finite granularity of money. But if you allow for a continuous price, there is no Nash equilibrium. So it's a bit tricky. In a continuous space state, 2 is not a Nash equilibrium for sure, because they split the market and player 1 doesn't want that. But 1.99 is no longer a Nash equilibrium, because 1.999 would be a better unilateral deviation. And 1.9999 will be an even better unilateral deviation. So there is no real value that makes player 1 happy. Okay. Another problem that is classical in game theory is applied to economics and also political systems is the Hotelling model. Hotelling is the name of the guy, so it has nothing to do with hotels, even though sometimes it's often confused because it has to do with, well, tourism and touristic services. So the model of competition proposed by Hotelling can be readjusted like this. So one way to rephrase it is the vendors of the ice cream stand. So assume you have a very busy beach boulevard. And there are 2 vendors of ice cream. And the 2 vendors of ice cream can set, well, either they have a trolley in some setup, so they can set the trolley somewhere along the street, or they can open a shop. They can open a stand. So it's not a trolley that can be moved continuously. So let's make it simple. There are, for the sake of simplicity, there are 101 possible locations. Maybe the boulevard is long 1 kilometer, and you can put your stand every 10 meters. For the sake of modeling, we make all of the positions within 10-meter range to coincide. So what happens when you put your stand for ice cream cones on the boulevard? The people will come to the nearest ice cream stand to buy an ice cream, right? Because, people are lazy while catching sun on the beach, so they want a refreshment, they go to the nearest stand. That's usual. It makes sense. Also, we assume that the ice cream stand are perfect substitute for each other, so they set the same price. So really, all that matters for the people buying ice cream is what is closer. There is no real difference in quality or price, because this is very realistic, I would say, in ice cream parlors at the beach. Really, there is no much difference in quality unless you compare Italian ice cream, of course, which is much better with American ice cream. But if you are on the same beach, you have 2 ice cream parlors, they have the same quality probably, and also the same price. Also, we assume the people distribution of the street is uniform. So you get the same, you attract the same density of people, but you stop attracting people when the other ice cream parlor is nearer. Okay, so for example, if vendor A chooses position 22 and vendor B chooses position 34, well, vendor number 1 gets everything from 0 to 28, and then from 29 on, parlor B is closer, so vendor B gets the client. This means that vendor A has an incentive to move to the right, because moving to the right will keep him or her the left-hand side, you see, and he will attract more customers from player B, correct? So what is the Nash equilibrium here? The Nash equilibrium here, actually, player A can also change. If vendor B chooses 35, player A can choose 36, right? Because the right-hand side of the street is bigger now. So there is another incentive to deviate. So you see that the only Nash equilibrium is that they both choose 50. They both choose 50, so basically one gets the left-hand side and the other one gets the right-hand side. So this is often used in political systems. Is actually often dubbed as the reason why the American political systems are very driven to the center. This ice cream model is often used as a metaphor for the political compass, meaning there are people very far on the left side, people very far on the right side, and a politician, actually politicians are liars, they just claim their views to attract more voters. So if, according to political system theorists, if a nation has a lot of the electorate that is on the left side, and there is no politician claiming the left side positions, Well, there will be one because it's convenient for a politician to position there and get some votes from that area. The point is that American politics are often steered towards the center. So if you see the debate, the presidential debate of the United States, they basically say the same thing. Well, nowadays they often talk over each other, but they say many similar things. It doesn't look like one is the left candidate, the other one is the right candidate. Maybe one is slightly more left, so is in position 49, the other one is position 51, but they are not really separate by any difference, any big difference. And this is often explained, according to the Hotelling model, by political system experts. They say, well, the center is so attractive and so powerful that when you have two ice cream vendors or two politicians, two competitors for the role of the president, there is a convergence toward the center. This does not happen in many European systems instead, where you have multiple parties, not just two parties. So in political systems, the electoral systems that are designed to have a perfect bipartisan situation, where you have two big parties, are inspired by this desire of having a center-oriented political line. Other countries like Italy, which in Italy is well known for having many, many parties. So in Italy, you don't have the situation. So you have sometimes some extremism in the position because there are maybe 3 parties or 4 big parties, and while 2 of the parties converge to the center, the other are left to capture the extremists. And this is often the case actually in Italy. You can compare the situation. I won't make any consideration, but very often when there are 3 or more big parties in Italy at any time, you see some 2 parties governing and the third party making some very extremist claim to capture a share of the population. And then this third party goes to the government and suddenly, and another one is left out, and suddenly the other one that is left out becomes very extremist because of this theorem. Okay, so this is actually very useful, but has nothing to do with engineering. Still, if you, instead of having ice cream parlors, you want to, I don't know, make some coverage of cellular systems over a city, you can use a similar model, for example. Or maybe you want to ensure service throughout the entire day. You can use a similar model. So you see there are many similarities that you can exploit for any project of yours.